Hello, this is your TA, Aldo San Pedro. I'm going to be covering problem 2.34, or number 19 from your extra credit set of questions for the upcoming exam. You can find this problem in your textbook in chapter 2, and it's going to be number 34. And just like all of the rest of the even numbered problems, you can find the answers in your appendix at the back of your book. Anyways, this question is going to be asking us to find out the probabilities of a couple having several children that might be affected by autosomal recessive. The question asks, a man and a woman are each heterozygous carriers of an autosomal recessive mutation. So it's going to be something, I'm going to be using little a, something like this, of a disorder that is fatal in infancy. They both want to have multiple children, but they are concerned about the risk of the disorder appearing in one or more of their children. So this problem states that the man and the woman are heterozygous carriers. So I'm going to be constructing a monohybrid cross to find the probability that any one of their children will have the autosomal recessive mutation. So when we do the cross, we get big A, big A, big A, little a, big A, little a, and little a. From this, we get 3 different genotypes, as you see here, but the phenotypes that are important in this question are whether or not that infant is going to have fatality or not. So I'm going to be splitting it into the phenotype ratios. So the chance of having mortality at infancy, represented by AA, is going to be equal to 1/4, as you see one pair of little a in this monohybrid cross. However, the chance of being unaffected is going to be 3/4. Now that I have this information, I can go to part A. Okay, so part A is asking us to determine the probability of the couple having 5 children with no children being affected by the disorder. So kind of conceptually thinking about this, I'm going to lay out more or less the desired outcome of this problem of the couple having 5 children with no children being affected by a disorder. I'm going to represent each child as C1, C2, where C equals child. I'm going to be using a check mark to denote that they are unaffected, and an X to denote that they are affected. So if we're having 5 children with no children affected by the disorder, they're all going to be unaffected. Now, to determine the probability, you might rush and say, oh hey, the chance is going to be 3/4. However, that is incorrect. We need to use the product rule to find the answer here. Before I kind of go into the shortcut of the product rule, I just kind of want to lay out the probability of each one of these independent events occurring. Next, we're going to be multiplying them. And to simplify this, we can say 3/4, that looks like 9, 3/4 raised to the 5th. Now this right here being used, where you're taking the probability of that event occurring and you raise it to the number of outcomes where that probability can happen. Now that we have our simplified expression, we can do the math. So whenever you have a fraction that's being raised to a power, for example 3/4 to the 5th, you're going to be distributing this exponent to the numerator and the denominator. So 3 to the 5th will be 243. 4 to the 5th is going to be equal to 1024. It's going to be equal to 0.237. That is the probability of our couple in question having 5 children with no children being affected by the disorder. Part B is asking us to determine the probability of the couple having, once again, 5 children. It's going to be this way in all the parts. But 5 children with 1 child being affected by the disorder this time. But before I go to that, I'm going to be covering a common mistake that people might make when they approach this problem. So kind of just like above, if you were to map out each child, you might say that child 1 is okay, child 2 is okay, child 3 is that one child that's affected, child 4 is okay, child 5 is okay, and then just like above, you write down each probability. However, that's going to be incorrect. Why is this incorrect? It's incorrect because we can distribute this X and these check marks in a certain amount of combinations. So for example, there's 5 different ways that this can happen. Now you can solve for the answer here now that you know your known combinations, and we'll do that, but after this I'm going to be showing you a shortcut through binomial probability. But this might just help to kind of show you what binomial probability is doing. I'm going to be putting these numbers back. If we are to solve for this and multiply each one, it's going to be equal to 81 over 1024. And then if we're going to do it again, it's going to be equal to 81 over 1024. Do it again, again, and again. Because these events are mutually exclusive, we can use the sum rule to add them all up, and we're going to get 405 over 1024, which is going to be our answer. I want to show you all the easier way of solving this, so you don't have to lay out these tables, do the sum rule. I'm going to show you a way to save all this time, because it's super easy to make mistakes right here when you're generating these tables. So time for the shortcut. So when you see a problem and you can identify in the problem that there's going to be a number of ways that you can rearrange a combination of the outcomes, you can use something called binomial probability. Now, if this question were to ask, determine the probability of the couple having 5 children with just the first child being the affected, then you would do something like this. However, we saw there's 5 different ways that can happen. You can use something called binomial probability. I'm going to be putting the formula here. You've probably seen this monstrous formula before, but working out this formula is a lot easier than deciding the amount of possible combinations that you can have. So for this formula, n is going to be the total number of children, x is going to be the total number of affected children, p is going to be the chance of the child being affected, and q is the chance of the child not being affected. Each of these exclamation points is going to be called a factorial, which is an expression. So for example, if we have 5 factorial, it's going to equal 5 times 4 times 3 times 2 times 1. It's just all the whole numbers under it multiplied against each other. Now that we know our formula, let's first identify each term and the number associated with it. So n, the total number of the children, that's stated here, 5 children. X, the total number of affected children, is equal to 1. P, the chance of the child being affected. Now remember, we figured this out up here. The chance of the child being affected is going to be equal to 1/4 in this case. For Q, the child of the chance not being affected, 3/4. Now, I'm going to put everything into our formula. And this whole expression right here is going to give us the probability that we're looking for. I'm going to simplify this. So our 5 factorial, 1 factorial is just 1 times 4 factorial times 1/4 to the first is equal to just 1/4 times 3/4 to the 4th. We get that from the 5 minus the 1. I'm going to simplify this further. We're going to be multiplying that by 1/4. And then, so 3 to the 4th is equal to 81. 4 to the 4th is equal to 256. Simplify, crossing out these 1s, crossing out these 2s, crossing out these 3s, these 4s. And what we're left with is 5 over 1 times 1 over 4 times 81 over 256. When we solve this out, we get 405 over 1024. When we simplify that, the answer is going to be equal to 0.396. Now notice that this 405 over 1024 result is the same result we got when we were putting in the x's and the check marks in all the combinations that we could get and using a combination of the product rule and the sum rule. As you can see, this method I feel is a lot better. Part C is asking us to determine the probability of the couple having 5 children with 2 children being affected by the disorder. Just with the problem above part B, there's going to be a certain number of ways that we can arrange the possibility of 2 children being affected by the disorder amongst the 5 children. So we're going to be using binomial probability once again. So I'm going to paste that again. N is equal to the total amount of children. X is equal to the total amount of affected children. P is the chance of the child being affected. And Q is the chance of the child being not affected. So M is equal to 5. We know that from right here. X is going to be equal to 2. We know that from right here. P is going to be equal to the chance of being affected, which is equal to 1/4, which we found through our monohybrid cross above. Q is equal to the chance of the child not being affected, so that's going to be 3/4. We're going to be filling out our formula. We'll be raising this to n minus x, or 5 minus 2. We know that's 3, so I'm just going to erase this and put a 3 there. Now, when we simplify this, we're going to get, just like with the other problems, we can simplify a bit. We're going to get 20 over 2 times 1 over 16 times 27 over 64. We can simplify this 20 over 2 to 10. When we do calculate this, it's going to be equal to 270 over 1024. When we simplify that even further, our decimal value is going to be equal to 0.264, the answer to this question, or the probability of the couple having 5 children with 2 children being affected by the disorder. Part D is asking us to determine the probability of the couple having 5 children with 3 children being affected by the disorder. So once again, this is going to be a binomial probability question because we can arrange those 3 children being affected among the 5 children total. You can build a table of sequences to find out the possible number of outcomes. However, it's going to be a lot of work. So we're going to be using the binomial probability formula. So we're going to be having the total number of children, which is equal to 5 factorial. We're going to have the total number of children being affected, 3 factorial, multiplied by the total amount of children minus the total amount of children being affected, which is equal to 2. And what we did here was just 5 minus 3. Anyways, that's going to be also a factorial. We're going to be multiplying this by the chance of being affected, which is 1/4. We're going to be raising that chance by the number of children that will be affected, which is 3. And we're going to be multiplying that once again by the probability of being not affected, which is 3/4. The exponent that we're raising this to is going to be equal to the total amount of children minus the total amount of children affected, which is equal to 5 minus 3. And just like with our inside value there in the parentheses, it's going to be equal to 2. When we expand this, we can simplify once again here, which is equal to 20 over 2, which is just equal to 10. We're going to be, carrying these terms down. So when we multiply everything together, we're going to get 90 over 1024. Our answer is going to be 0.0879. And also be careful here. It's asking us to express our answer to 4th decimal places. Whereas over here, you can see that part C is asking us to do 3 decimal places. Going down to part E here, asking us to determine the probability of the couple having 5 children, with 4 children being affected by the disorder. We're going to be using the binomial probability to swiftly find out our answer. Raising it to 5 minus 4, or equal to 1. I'm just doing the simplification here just to speed things up, and I can do that over here as well. Simplifying this, we can simplify here. We get a 5 over 1 times 1 over 256 times 3 over 4, 15 over 1024. And when we express this answer to 4 decimal places, it's going to be equal to 0.0146. Now, I already gave you a hint for part F. Part F is asking us to determine the probability of the couple having 5 children, with all children being affected by the disorder. As you can see here, I wrote that there's only one way to distribute this, so we're going to be using the product rule. To illustrate this, the probability of the couple having 5 children, with all children being affected by the disorder, there's only one way to organize this. If we're implicating that a child being affected is with an X, and we have 5 children, you can't distribute these X's amongst each other like we did when we had a check mark. So there's only one way to do that, so we can use the product rule here. So the product rule states that we just put our chance in question, which is the chance of being affected, raised to the exponent of how many times it's going to be happening. So we're going to have 5 times for all 5 children. It's going to be equal to 1 over 1024, and our answer is it's going to be equal to 0.00098. Anyways, I do want to illustrate one thing here. Going back to part A. So what if this question instead asked, what is the chance that at least one child is affected? What this problem is asking is, what is the chance of at least one child affected out of the 5? I use the greater than or equal to symbol here because we can have in this question where at least one child is affected. We can have 1 child affected, 2 children affected, 3 children affected, 4 children affected, or 5 children affected. One way you can quickly figure this out, where at least one child is affected, is to take 1 and you subtract this, the chance of all individuals being not affected. So the chance that all individuals are not affected by the disorder here, just like we did in part A, is going to be equal to 3/4 raised to the 5th. And, you can see the parallel here. When we solve this out, we're going to be getting, this further simplifies to 781 over 1024. So this question were to ask us, what is the chance of at least one child being affected? It's going to be equal to 781 over 1024. And whenever I see that at least, I like to immediately think of